Okay, I think we're ready to start. We're going to be talking about Spice Frontier, a real-time frontier. My name is Sean Dunn. I'm the Chief Technology Officer of Steamroller Animation. I've been in the industry for many, many years, and I've been very lucky with the roles I've had. I've worked on the software side, I've worked on the production side, I've worked on the education side. So I've worked for companies like Alias Wavefront, when they were developing Maya back in the 90s. And then I've also worked for Epic Games, helping with Unreal Engine as linear content. And then I've also worked in production. I worked at Weta Digital, and I was fortunate enough to work on, movies like Lord of the Rings and Hobbit and Avatar and, slew of others. What I'll do is I'll give you a bit of an introduction of what Steamroller Animation is and what the company is. So we're a studio that, we believe in flattening the boundaries and elevating artistry. We work really hard to do the best quality, work that we can. We've got a broadly talented team spread out, among the actually all over the world, in fact. And this is a video of the company introducing it.
At Steamroller, we are super excited about the craft of animation. We love working with our incredible partners around the world, helping to support them with animation services as they bring their amazing projects to life. We also love creating our own original content. Our team is working hard on a number of new stories as we continue to build our animation pipeline, leveraging the power of the Unreal Engine. We want to thank our crew of artists, technicians, and support staff, and we hope you appreciate the amazing work they do.
I'm in.
Kent, did you just open your helmet?
No, that would probably hurt. Just something stuck in my throat. In my helmet. Hey, this is fun. Look at me out here doing this, huh? Come on.
The sensors show no motion or any heat signatures, but I think you should head back to the ship. I'll take over from here.
No. I've got this. You just said there's nothing on the sensors, so let's not get carried away. I've got my blaster. Ugh.
Okay, so You can see we've quite a range of projects that we've worked on. What we're here to talk about today, though, is Spice Frontier. So at the end of that, you would have seen some Spice Frontier shots. So we did a trailer in 2020, and that's what you would have been looking at there. That would have been done in Maya, typical offline rendering pipeline. Whereas Spice Frontier is something that we've been doing in Unreal Engine, and so I'll show you a clip for introducing it.
Imagine a human chef and his alien crew on an epic quest across the universe after the destruction of Earth 250 years ago.
Wait, what?
Chef Kentucky Williams has a dream of astronomical proportions.
Imagine this. Restaurants and food stalls as far as the eye can see.
Kent and his crew aboard the Serrano are traveling through strange alien planets, searching for the lost ingredients of Earth cuisine. His mission is to unite the alien civilizations of the known universe through a shared love of food by recreating humanity's lost recipes. Welcome to the universe of Spice Frontier. This beautifully imagined, visually stunning universe is being developed within a brand new real-time pipeline, leveraging the power of the Unreal Engine. Our team is continuously developing proprietary lighting, rigging, and animation tools that will redefine the creative and technical process of linear storytelling in a real-time environment.
I think some of it got in my suit.
Steamroller Animation is a self-funded studio with a global footprint of more than 230 team members.
Well, it's not too bad. Aside from cosmetic damage, it looks like we just lost an engine coil.
The pilot episode of Spice Frontier has a running time of around 25 minutes and features nearly 400 shots across 9 sequences. Will these spice hunters be able to survive when they themselves become the hunted? Will Kent realize his dream of an Earth cuisine renaissance? Or does his true destiny lie elsewhere?
There we go.
See how the Spice Frontier saga unfolds. Coming soon from Steamroller Animation.
Come on, there we go. Okay, so that's a taste of what the episode is going to be. The project itself, it's meant to be a family-friendly adventure, young adult demographic. It's a very stylized 2D look that we've managed to get out of the engine. It's a 25-minute pilot episode, and it's real time. Some of the things that are important to understand with this is a lot of what you saw there was directly out of engine. So what we did was we got to a certain point with production, and we were looking at the images, and we were going through the normal nuke process where you're sweetening up the images, and so we ended up taking the images back into Unreal and seeing if we could match that look. And we were able to, get what we wanted in there, which was really important because what I didn't want to have a, rendered out project that is completely different than what you see in Unreal. Because if we wanted to use it anywhere else, whether it's VR or AR or in a game, you want it to look as good as it did in the renders. And so that was what was really impressive was we were able to get the look that we wanted. And as far as the real time part, it was working with the team and convincing them that Unreal is the direction that we want to go in. So the production's been happening for about 2 years, and when obviously it's a big step to be going from a more traditional pipeline and going into Unreal. Anyways, the real-time part became really important because it, and like I'm sure a lot of you're aware of, being able to get those visuals in front of people, getting everybody on the same visuals, getting lighting happening as early as possible, getting, all the different pieces so that, you can understand and see the visuals, and everyone's on the same page. And so it's been really important for us to kind of dive into Unreal and use that as the basis of our pipeline. Because from my standpoint, real time is sort of where things are going, and getting on board with a a tool like Unreal and understanding it and getting your talent pool educated on it and getting them up to speed on it, then it gives us, the ability to really make great projects in a timely fashion. And so I will pass it over to David here, and he'll kind of do a bit of a deeper dive for things. There you go.
Thanks, Sean. So kia ora koutou. My name's David Elvey. I'm the CG Technical Supervisor at Steamroller Animation. I've been working with Unreal for the last 9 years or so. And the last 4 years, I've been able to really heavily focus on building workflows specifically tailored to linear content or long-form narrative content. So today we're going to explore the critical question of how do we leverage Unreal Engine to create that linear narrative content. And in this session, we're going to break down some key workflows, including a fundamental problem that we all have to deal with, how we structure Sequencer, the tools that we've developed, and the workflow that it allows us to scale production efficiently. So as Sean showed, the Spice Frontier short has a distinct visual style that has served as the foundation for what we want to achieve. And as you can see from this concept art, our key inspiration was drawn from the aesthetics of classic 2D animated films, where the characters are flat and cel-shaded, while the backgrounds maintain a more volumetric or painterly look. And during production, we faced two primary challenges. The first is nailing the visual style that we had envisioned, and the second was transitioning to Unreal as our core production tool. So before diving into our creative process, let's first address what I believe is a challenge that every studio faces when they want to adopt Unreal Engine for linear content. So on one side, we have traditional CG artists, and these are experts in linear content creation who have a deep understanding of the visual and storytelling demands of animation. And on the other hand, on the other side, we have real-time specialists. So these are people coming from game development with the technical knowledge of Unreal Engine. And we might think that since both sides share common ground, so we're working with models, textures, materials, lightings, and effects, that the transition would be pretty straightforward. But the thing is, this familiarity can lead to a false sense of security, where while the skill set is somewhat transferable, the mindsets and approaches to problem solving can be strikingly different. So I'm curious, does anybody here, would they put themselves into the game artist circle, coming primarily from there? Not too many. What about the CG artist circle? How many people come from that circle? Yeah, okay. And does anybody think that they kind of living in that hybrid world in between? Okay, so a few people. So those people there might kind of have already experienced this push and pull between traditional CG and real-time approaches. But depending on which side of the fence you're on, the way that you approach the same problem might differ quite dramatically. And that brings us to two critical questions that we need to ask ourselves, which is where in production do these approaches or mindsets diverge? And how do we reconcile those differences to create a cohesive workflow? So what we're sharing today is the culmination of wrestling with those opposing forces, the convergence of real-time and linear content. And while the journey hasn't been without its challenges, we've found that embracing this fiction has led to some truly exciting results. Perhaps the most important workflow challenge that we've had to overcome is our shot build process. So when producing linear content, how we work with and structure Sequencer had a massive impact on the entire production. Sequencer forms the core of our workflow in Unreal, and we need to create a stable platform for our Unreal artists to work within. So we can start by looking at the traditional approach for structuring Sequencer Unreal, which generally follows a top-down hierarchy. And typically that workflow might look something like this. At the top, we start with a sequencer representing the episode. Nested within this are scene sequences, allowing us to make high-level adjustments that impact every shot within that sequence. Underneath the scene level, we have sequences for individual shots. And finally, there may be department-specific subsequences, allowing different teams like lighting effects, animation, etc., to manage their respective elements. And this top-down approach makes sense at first. It allows us to create changes at a high level that propagate down through the nested sequences. However, we've found that this system comes with significant drawbacks when scaling. So let's say that we want to work on or render a specific shot. To make sure that we have all the necessary overrides and settings, we need to not only load in the shot, but also the entire scene as part of. And as soon as we load in the scene, we're now loading all of the shots in that scene along with their respective departments. And we found that as you kind of get bigger and bigger, this starts to scale poorly. If we only want to focus on a single shot, we're forced to load in a lot of data from all of these other shots. And this creates memory constraints, slows down the workflow, and limits what we can do within any one particular shot. So what is the real challenge that we need to solve? We need a system that retains the benefits of the hierarchical overrides, allowing us to work at a high level and apply changes across multiple shots, while also minimizing the overhead. The ideal system is going to allow us to focus on individual shots without loading unnecessary data from other parts of the scene. And so to solve this, we developed what we're calling the Shot as King workflow. We've been working with this system for a couple of years, but we have seen other teams and artists beginning to explore similar ideas. So in this system, everything lives within a shot context. We do want to retain the idea of hierarchical overrides, and we still group shots within a scene to an override to be able to apply changes across multiple shots. But here's where our key difference is. Instead of nesting shots inside the override sequences, we nest override sequences inside each individual shot. So here's how that looks practically. Each shot is built in isolation, so at any point we can work on or render it without loading anything else. We continue to use steps to break down the work required for a shot, and this allows different artists to work in parallel. And here we're creating a folder for a particular step, the environment step. Note that we move towards calling them steps instead of departments. One of the great things about Unreal is that it allows our artists to become more generalists and work across departments. So these groupings now become more about the type of work being done rather than the traditional department that is doing the work. Each step has its own set of subsequences for each override, and this keeps workflows segmented and organized. For Spice Frontier, we established two main layers of overrides. We have masters. These are collections of shots that share the same spatial location, and groups. These are subsets of the masters where we group shots that are similar in camera angle or framing. And this allows us to apply broad changes at the master level and then refine them at the group level. We also have a third override, which is just for the individual shot adjustments. And then another issue we had to tackle with the setup is how Unreal handles priority when we have multiple overrides that are affecting the same object. So in the traditional system, priority is determined by the depth of the sequencer in the hierarchy. So the deeper the sequences, the higher the priority. In our new system, however, nesting overrides is going to create conflicts. So instead, we use sequencer's hierarchical bias to manually control priority. So we set the bias of 1 to the master, 50 to the group, and 100 to the shot. And this ensures that changes in the shot override always take precedence, followed by the group and then the master. So by restructuring the workflow in this way, we've created a system that keeps the benefits of the hierarchical overrides while giving us the flexibility to work on each shot in isolation. This shot as king philosophy not only improves performance and scalability, but it makes it easier for our artists to focus on their individual tasks while working in parallel with other artists. So now that we've explored the workflow itself, we can have a look at how we've automated this process with our shot setup tool. So here's a screenshot of Unreal, and we have our tool docked on the right-hand side. The tool is connected to Flow, which is our production tracking solution, and it's fully configurable per project. The main purpose of this tool is to automate the entire shot setup process, and it streamlines the workflow that we just covered, and it does a few extra things as well. So we're going to jump into a quick demo of building that shot. So we're going to set the context to scene 10, shot 200. And once we've done that, we can go ahead and update the sequencer. This will automatically create the sequences, add the necessary overrides, and add the camera actor, followed by what we've discussed with the shot as king structure. Then we can import the camera animation directly into the shot, and you can see how quickly the shot is built up with everything that's synced up. As the shot evolves over time, artists can continue to update it, and the tool ensures that everything is kept in sync with the data and flow. Because the tool is context aware, it can also handle additional functionality, like in this example, we're importing the camera animation. There's a lot more that the tool can do, and we're going to continue to look into some more of its features a little bit later. So at the start, I mentioned how there are differing mindsets between traditional CG and real-time workflows, and that they brings unique challenges. One of the main conflicts that we had for us was our character workflow. So we're going to move on to have a look at that now and how we solved that problem. So the main challenge here was character versioning. So in Unreal, it's common to import a skeletal mesh once and update it by re-importing the same asset. We keep a single representation. This ensures memory efficiency and animation compatibility. However, in traditional CG animation, rigs often need to evolve as the production progresses. As new shots are worked on, rigs are modified to address specific animation needs. And this creates a challenge. How do we update characters for future shots without breaking or reauthoring animation that has already been approved? We also need to handle variants, which are different representations of the same character. So for example, a character may have a different variant, a default variant, and then a variant where they're all roughed up a bit. Each representation of the character is treated as a different variant, but it's still the same asset. The third element to consider is components. Components are parts of the character that do not require a full variant, but they can be treated separately depending on the needs of a shot. These components are split into separate skeletal meshes and allowing us to have individual control of them during production. But as I mentioned, the most complex of the three was versioning. So to manage this, we created a versioning system that links the two files which are exported from Maya. We have the skeletal mesh file, which is imported into Unreal. This file only versions up when there are structural changes to the skeleton or to skinning. And we have the puppet file, or the Maya rig, which is passed to the animators. And this file updates more frequently, and as the rig evolves during production, to accommodate the needs of the new shots. The puppet file contains metadata that tracks the version of the Unreal skeletal mesh that it is compatible. And as you can see, we can have multiple puppet files linking to the same skeletal mesh. So when animators work on their shots, this metadata is embedded into the published animation file. And upon importing, Unreal uses this metadata to automatically assign the animation to the correct skeletal mesh version, ensuring compatibility without the risk of version mismatch. And so to bring everything together, we've developed a custom dynamic character system. So instead of loading all of the character data, the dynamic system ensures that we load into memory only the skeletal mesh assets that are needed. And this improves performance throughout production. The solution keeps our character workflow flexible and fully integrated with our animation pipeline, and it allows us to iterate and update rigs without disrupting previous work. Now, so we're going to circle back to our shot setup tool and see how that automates the process of bringing a character into a scene. So first, the tool checks what animations have been published for the current shot. As part of our workflow, all characters are initially spawned into the anim step shot override. Once we use the setup character buttons, the tool automatically spawns the correct character blueprint and assigns the relevant animation. So when importing the animation, the tool auto-detects the correct asset and skeleton, ensuring that the animation is assigned to the right version of the character. And so one of the major advantages of switching over to Unreal Engine for linear content is how flexible its systems are, especially when you start combining C++ and blueprints. So I want to talk through how we use both to build elements of a custom dynamic character system. By highlighting a few features and tricks that we used to build this custom workflow, I hope to show how Unreal's can solve this for us. So it might get a little bit technical for artists here. So at the foundation of our character system is C++ class, and this provided the power and flexibility we needed to make the system reactive to data inputs. We're not using C++ for any runtime specific logic, but instead we use it to access some functionality that isn't available in native blueprints. Specifically, we wanted the system to respond dynamically to information that is passed into it. So in our workflow, we use data assets to define asset variants, and each variant data asset holds the information about the version information about that character. These data assets are linked to the character blueprint, which then builds the character dynamically based on the settings provided by the user. When an artist spawns a character, the system needs to automatically generate what variants and versions are available from the data assets, and this allows the user to select valid options for the character. And so to do this, first in our base C++ class, we create some properties. One here we have defined the available character variants, and this is just the T array of that custom data asset that I mentioned. Then we have two additional properties that will serve as a drop-down box to select specific variants and versions. And then to ensure these properties can be used in Sequencer, we add the specifier into it. Then we create functions for each property that we want to create a drop-down box for. And then on the property, we add the getOptions specifier, and that points to the specific functions that we created. Finally, the function's job is to return a T array of options based on the state of the character, which in turn is going to populate the options in our drop-down box for our properties. And this means that rather than manually typing in a version, artists are provided with an automatically generated drop-down list of valid options. And by using C++ as a foundation, we ensure that all data is accurate and dynamic, creating a reliable technical backbone for our artists to work with. So here's what the property looks like in Unreal when you use the getOptions flag. You get a nice drop-down menu. So with our base system set up in C++, we need to ensure that the characters can integrate seamlessly with Sequencer, which is critical for animation and timeline management. Sequencer is designed to work with skeletal meshes, but we want the flexibility of a blueprint system for handling multiple character versions and modular setup. A neat trick is that by making the root component of the class a skeletal mesh component, and then assigning a skeletal mesh asset to it, Sequencer is now going to treat that blueprint like a skeletal mesh asset. And this allows us to leverage all of Sequencer's animation functionality while retaining the functionality of the blueprint system. So once the system's base functionality was set up in C++ and integrated into Sequencer, we could then extend it further with blueprints to make it more user-friendly for our team. And we're going to have a look a little later at some things we did within the blueprint to extend the character system functionality. So now we're going to have a look at our character art style, where we wanted to invoke the classic 2D look. To do this, we settled on a flat shaded aesthetic, intentionally withholding volumetric lighting from the characters to maintain that 2D feel. We start with an emissive material as the foundation. This gave the character a flat cartoon-like appearance. However, to avoid making them look completely flat, we added subtle shadows painted directly into the textures. And this helped elevate the aesthetics while retaining that 2D quality. Next, we enhanced the look by adding directional rim lights. In this shot of Kent, for example, we have two rim lights working together. So first we established a directional rim, which uses a modified silhouette offset technique. We then fine-tuned attributes like brightness and color to match the shot requirements. And finally, we control the fade off by applying a vertical gradient to the opacity, and this creates a smooth termination and taper effect. So we're going to break down the modified silhouette technique, offset technique with this example. You've got a very simple circle. So instead of offsetting the character silhouette to create the rim mask, we instead offset the depth pass and do a depth comparison between the original and the offset. The more we offset, the thicker the rim effect becomes. And here we're also defining the direction of the offset, which controls where the rim is going to appear. So if we now assume that the circle is at depth of 10 and the background is at 10,000, we can sample the depth values. At points where both the original image and the offset are at a similar depth, sort of like in the middle of the circle, we get a very little depth disparity. The depth values are both around 10, so it results in a very small difference. In the top left of the circle, the original value is 10, but the offset is way in the background at 10,000, and this creates a massive positive depth difference. And at the bottom right of the circle, the offset value is 10, but the original is at 10,000, and this creates a massive negative depth difference. After calculating the depth difference, we discard any negative values because these represent depth disparity in the wrong direction. And then finally, we set a threshold and clamp values. Any pixel with a depth difference greater than this threshold becomes part of the rim. Setting the threshold allows the artist to control how much depth difference is needed to determine where the silhouette becomes visible. And by comparing the depth values instead of the silhouette, the system is now also able to include internal edges to the rim as well, not just the silhouette. So here again, we have Kent with the rim applied. And then because our character is using an emissive material, they don't naturally inherit standard shadows from the environment. So to simulate more dynamic lighting effects, we developed the Gobo system, which allows us to project an art-directable shadow texture directly onto the character. This allows us to precisely control how the shadows behave on the character, adding another layer of visual depth without losing that flat shaded look. So here's a shot in context, and you can see how these different techniques, the emissive materials, subtle shadows, rim lights, and Gobo systems, all work together to create the final look. The characters stand out clearly against the background, yet integrate smoothly into the shot. As we've just mentioned, we have the Gobo set up to add shadows to our characters. So we're now going to have a look at that system. In this shot, you can see we have shadows interacting with the character. There is a shadow layer indicating the window of the ship, as well as scrolling shadows moving across the characters that indicate movement. These effects are all driven by our Gobo system, which, as I mentioned, projects painted shadow maps or Gobos onto the characters to simulate environmental interaction. The system is comprised of 3 components. We have the Gobo actor, we have a scene manager, and we have our aforementioned character blueprint. The Gobo actor is placed in the world and defines how the shadow map is projected. It contains a camera component that sets the projection parameters such as transform, field of view, and aspect ratio. The artist assigns a specific Gobo texture, such as the window shadow in this case, which is then projected onto the character. Each Gobo actor is given a unique ID, allowing the system to track and assign specific Gobos to characters or groups of characters. The character blueprint plays a key role in passing information to the character's material, and it's in the material where we handle the actual shadow projection calculations. So on construction, the character blueprint creates dynamic material instances for the character's materials, which allows them to be updated dynamically. Whenever the Gobo updates, the camera information, such as the position and the projection settings, is passed to the materials through the character blueprint, and this ensures that the shadows are always accurate and responsive to the movement of the Gobo actor. Once the data is passed through, the material calculates screen projection UVs based on these projection settings. Finally, we have the scene manager, which plays a lightweight but crucial role. It acts as a persistent bridge that allows the Gobo actor and character blueprint to stay connected and share information, even when they're spawned dynamically. Without it, the dynamically spawned Gobo actor and character blueprint won't be able to communicate effectively. So let's have a look at how the material works for this. So here the characters appear without any environment shadows. They look great, but they feel disconnected from the world. So next, the character blueprint passes the camera information to the material, and this generates dynamic UV coordinates based on the Gobo actor's projection settings. These UVs are updated in real time as the Gobo actor moves or updates. And here we can see the UV coordinates that are generated for the characters. Once the UVs are generated, these are used to project the shadow texture onto the characters. And here we can see how the shadow mask is applied. Finally, using the ID setup, the Gobo actor can project to a specific character or across multiple characters. In this case, we have a unique Gobo actor per character, but one Gobo actor can be applied to multiple characters if needed. Finally, we can see the shadows fully projected onto the characters, simulating the interaction between the characters and their environment. So that's without the Gobos. That's with the Gobos. So the Gobo system gives us incredible artistic control over how shadows are projected onto our characters. And by dynamically creating UVs based on camera information and allowing real-time updates, we can achieve the stylized 2D aesthetic that we want while still ensuring characters interact naturally with the environment. Like the rim light system, this approach provides both precision and flexibility for art direction. So when working with blueprints in Sequencer, it's important that we understand how properties are set and how that can affect performance and functionality within your blueprints. In our character blueprint, because the character is dynamically built when it spawns, there is a lot of logic that runs to generate the character. The same construction script will run every time a property is updated in the details panel, and that's going to rebuild the entire character from scratch. And while this is fine in some cases, it can become inefficient and isn't really an ideal solution. Additionally, when we expose properties to Sequencer, you might initially rely on rerunning the construction script when these properties change by enabling a setting in the blueprint class called run construction script in Sequencer. While this will ensure that your blueprint reacts to Sequencer updates, it does mean that the entire construction script runs every time a property is changed. Again, not an ideal solution. For example, with our Gobo setup, when new information is passed in, we only want to update the materials related to that change. We don't want to rebuild the whole character. So a more efficient solution is to use blueprint setters. These intercept the property changes directly without rerunning the construction script. And we're going to have a quick look at how that's set up. So first, we want to turn off the run construction script and Sequencer option. Instead of relying on the construction script to update the blueprint, we're going to create a setter function that is called when the property changes. We create a variable and make sure the property is set to instance editable, and also want to set exposed to cinematics. This allows for it to be added to the Sequencer track. Simply exposing the variable isn't enough since we've disabled the run construction script option, so now we need to create a setter function. And setters are common programming techniques used in many languages to control what happens when a property is modified. In Unreal, we can override the default setter behavior to allow us to control how a property is set, and it gives us fine control over that behavior. So now we want to create that function and set some specific settings. The function must be named set with a capital S, followed by the exact name of the variable, and this is case sensitive. So this allows Unreal to recognize that this function is tied to a specific property change. In the function's details panel, we want to tick the call and editor option so that it can be triggered in Sequencer and in the editor. And then we want to create an input for the function that matches the type of the variable exactly. So if the variable we're changing is a float, then this input needs to be a float. The name of the variable here, the input doesn't matter, but the type is very specific. And note that it's important not to add any additional inputs to this function or change the input type, otherwise the setter won't work correctly. Then in the setter function, the first thing we need to do is ensure that the input value is stored into the variable itself. Because we are overriding Unreal's native setter, that is not going to be stored anymore, so we need to make sure we store that value. And after that, you can implement any additional logic that you wish. For example, in our case, we are simply adjusting a parameter on the material instance based on that new value, but you can extend this to any additional functionality that you need. And by using setters instead of relying on the construction script, we gain granular control over property updates. This means that when Sequencer changes a property, only the relevant functionality, so for us adjusting a material parameter, is executed, not the entire construction script. This greatly improves the efficiency of your blueprints in production and is especially useful when working with complex, dynamically built systems like our character setup. So Sean mentioned that one of our goals with Spice Frontier was to adopt as much of an Unreal workflow as possible while still maintaining the unique 2D look. So the last thing we'll look at today is how we use the hybrid approach for our effects, blending traditional 2D hand-drawn animation with in-engine real-time rendering. So here's a shot from the show where we used hand-drawn 2D images for things like the thruster effects and the environment effects. The biggest challenge with this was how do we get our 2D hand-drawn effects sequences into the engine for our Unreal artists to use. For our solution, we created an effects projection system which allows us to achieve this result. So now we're looking at a specific frame of the shot. And our 2D effects were created by some amazingly talented artists in Toon Boom, where each effect was drawn frame by frame. To allow for more control in Unreal, we separate the effects into layers, grouping by elements and depth. These layers are then exported as image sequences, providing flexibility for compositing. To bring our 2D effects into Unreal efficiently, we pre-processed the image sequences into sprite sheets. This ensured that the entire sequences could be represented in a single texture per element, and optimized memory usage and improved performance. A key part of this process was calculating the smallest bounding box that could contain an entire effect on each frame. Using OpenImageIO, we analyzed each frame to determine the minimum space required to encapsulate all the valid pixels. Once the smallest bounding box was determined, we then cropped each image to this region and created a sprite sheet layout. To maintain memory efficiency, we ensured that the final sprite sheet adhered to a power of 2 texture size, and this was a pretty crucial step, as using a power of 2 texture allowed us to optimize the use of texture memory. Doing this means we could leverage maps in the editor for better performance during iteration, while ensuring that the full-size texture was loaded at render time with the highest quality. Without this solution, we found that many of our shots were too heavy to work with, just due to the sheer size and number of the effect sequences. In addition to this sprite sheet, we stored information about how the image was cropped so that it could be accurately replicated in Unreal. Once it's imported into Unreal, we used our custom effects projection tool to align the effects with the camera. This tool converts the screen space coordinates from 2D sequence into 3D space, allowing for depth layering and seamless integration with the 3D environment. Doing this ensured a pixel-accurate projection. Unlike traditional sprite cards, this approach gives us precise control over where the effects sit in the frame or in screen space without distorting the image. And each layer of the effects can be positioned to the correct depth, maintaining the illusion of 2D animation while blending with the 3D world. So by integrating 2D hand-drawn effects into Unreal with the projection system, we've maintained the traditional look while gaining the flexibility to iterate directly within the engine. And this allows for fast reviews, consistency across shots, and precise compositing of 2D effects in a 3D environment. So where to next? The Spice Frontier project has been an amazing journey where we've had laid a solid platform for building linear narrative content using Unreal. It would be a lie to say that it has been smooth sailing, but I think with this foundation set, we are starting to see the benefits that Unreal has to offer linear content creation. If you want to follow along with the progress of Spice Frontier or any other content from Steamroller Animation, please subscribe to our YouTube channel. We've currently got a series of production diary videos and various other things to check out. The original Spice Frontier short has also been uploaded, so if you haven't had a chance to check that out, go to the channel and you can have a look at that. So that's it from us. I hope you've enjoyed the talk, and thanks from the whole team at Steamroller.